Wait. What? I know.
Okay, were there any questions on any of the reading topics for today, if you did them? So there will not be a quiz on Friday, because I know people are all over the place, that I still will be having class. I will record it, although you never know, the computer might have a malfunction, and so you might miss something. So it's always good to be here if possible. And I'm going to try and get your exams done. I may post the answer key at least today, but if I do that, then hold off until you get your exams lobbying me for points. And don't ask me how you did, because I will say 10 points better than you did after asking me how you did. So I will try, and if you're not here on Friday, then you could always, if you're not in an undisclosed location where you can't email, you could always email me and I can scan it and send it to you. But I'm going to try. Everything is due on Friday that doesn't relate to class as well. So okay. Couple things I want to just kind of go back and mop up here, and then we'll talk about the topics for today, which lead into electrophilic aromatic substitution, which is going to be Friday, and then when we get back. And when we get back, there won't be any quiz either. I'll be probably lecturing, so there's nothing for you to watch, although I will put some stuff online. First was the idea of doing allylic free radical halogenation, because this is going to lead into the reactions. We're going to talk about what you do with the chain that's attached to the benzene ring. And unfortunately, the chain that's attached to the benzene ring has a couple of new reactions, but then it's got a lot of old reactions. So to lead into that, here is a double bond with an allylic carbon. Now the problem here is that we would normally try and do free radical halogenation with bromine light and room temperature. HV is the same thing as light, so room temperature. But the issue here is that free radical halogenation is a slow reaction, and bromination is rather quick. So if I try and do free radical halogenation using the conditions that we talked about in the past, instead of putting a bromine at the allylic position, which I will talk about is as selective as a tertiary position, instead what the bromine is going to do is add to the double bond 100% trans. So you may have wanted to add a bromine and substitute for a hydrogen on the allylic position. You're not going to do that. Instead, what you're going to do is you're going to do bromination, and that's not what we want with bromine, light, and room temperature, because you see those conditions, you immediately think free radical halogenation. So this introduces a new reagent that was back in chapter 19, which everybody has, or chapter 18, which everybody has access to, so you may want to go back, and I'll try and put that into the reading assignment for today. But I need something that's not bromine that won't add to the double bond if I'd like to do free radical halogenation. And that reagent is actually called NBS. So if I add NBS, and I'll write its structure out here, usually it's NBS and heat. What it will do is it will halogenate, and it usually halogenates in the same selectivities as what we found last semester. Remember that in terms of the selectivities for bromination for Br2, that for a tertiary position it was 1700 to 80 to 1. For secondary it was 80. No, sorry. It's 1700 to 80 to 1 tertiary to secondary to primary. So what does that mean? That means that you form a carbocation, a tertiary carbocation in bromination 1,700 times faster than a primary, 80 times for a secondary radical, or you form a radical, tertiary radical 1,700 times, secondary radical 80 times faster than the primary. Now, for bromination, which is kind of what we're going to do here, at room temperature, and this is bromination at room temperature, that means that if you have a tertiary hydrogen in your molecule, that's where the bromine's going to go. Because in order to break even, I would need 1,700 hydrogens to counteract the 1,700 selectivity. That's not happening. So our selectivity then is bromination will add the bromine to the tertiary position first, and then if there's no tertiary position, it'll add it to the secondary. If there's more than one secondary, it'll add to the secondary with the most number of hydrogens. And if you don't kind of remember that, you can always jump back. Everybody has access to last semester's Canvas. You could go back and look at that at the end of the semester. I'm not going to go through the math other than to just say tertiary is our most selective position for bromination. Now, what rivals that is an allylic position. So if I'm going to brominate with a double bond, the bromine's going to very specifically go to that allylic carbon. So if I use NBS, I'm going to exclusively at about 1,700 to 1 brominate that allylic position. So this is a way to brominate at the allylic position. And then from here I could do a lot of things. I could use an E2 base like tertiary butoxide or NH2 minus, and I could form the conjugated double bond off that. We've already seen that you could react this with water and replace the bromine with an OH. Our problem there is we're going to get a kinetic and a thermodynamic product. I could, if I wanted to, just along that line, I could say, you know what, I don't want to mess with kinetics and thermodynamics. How about I just do this? How about I just do hydroxide? And if that's the case, then we're more likely to have an SN2 reaction. So then I could substitute the bromine with an OH group. But if I used water, if I used H2O, then I would get a mixture of the kinetic and the thermodynamic products. So if I just want to do an SN2 reaction, use a strong nucleophile. So the bromination here, the critical part is that if I'm going to brominate at the allylic position, number one, I can't use bromine and light because the bromine will add to the double bond. And it will specifically go to the allylic position. Why? Because I'm going to form an allylic radical, and that allylic radical is stable because of the resonance structures I can draw. Now, what I usually do at this point is I ignore the fact that if you wrote the resonance structure for this, you would have the dot here and the dot on the primary carbon. So it's possible to get a kinetic and a thermodynamic product out of that. So what we do is we just ignore that by not talking about it, which unfortunately I just did. So we're going to ignore the fact that you could get a kinetic and thermodynamic product, and we're just going to say, you know what, if you brominate this molecule, it's going to go there. But you've got to use NBS. So what is NBS? NBS is N-bromosuccinimide. Okay, that's the chemical structure of NBS. And when you heat NBS up, it basically creates a bromine atom that does not add to the double bond. It just simply does free radical halogenation. Again, ignoring the idea that when we did an anti-Markovnikov addition, our Br dot added to the double bond to add HBr anti-Markovnikov. We're again ignoring that. I shouldn't have brought it up. This Br dot is just going to do free radical halogenation. So it's going to add a bromine there. But it will not produce molecular bromine that would add to the double bond. So you can use NBS or Br2 and light to do free radical halogenation on an alkane. Either one of those would be okay. But when you have a double bond and you want to brominate at the allylic position, you need to use NBS. That's what you need to do, and it's NBS and heat. So I think that's in chapter 18, which is why when somebody asked about it for the exam, I said, well, I put it on Piazza, and if you're not on Piazza, you should be. I haven't looked to see who hasn't logged in at all yet, but spare me the sadness of looking there and going, this person hasn't even logged in yet. Look at all they're missing. But then it was in chapter 18, so I wanted to go back over it. So could it be on the next exam? Yeah. Okay, so that's the difference between trying to brominate at the allylic position. And the allylic position is special because that's where the carbocation forms, that's where the radical forms. Okay. So NBS is an alternative reagent, but it could very easily be used on, it can be used on alkanes as well. Okay, is everybody kind of okay with that? So that will basically make this kind of molecule. These allylic bromides are what are called lacrymators. I've only ever made these things once. Lacrymators, let's see, things that are lacrymators for 100. Onions. Organic chemistry. Things that make you cry. So they are compounds you have to use in the hood. I remember when I did that, I had to put everything in a plastic bag and put it out in the hallway because I didn't want the cleaning staff to go in and have to be exposed to them. I made sure they were all wrapped up before if I had a paper towel or anything like that. So they're pretty potent lacrymators. Okay. So when we brominate, we're going to brominate at the allylic position. Now, why am I going back and talking about that? Because in an aromatic compound, when we're talking about the side chain, and by the side chain I mean the alkyl group that's attached to the benzene ring, this carbon is not the allylic position, it is called the benzylic position. And so the benzylic position then is the special position for a benzene ring. That's where the carbocations are going to form, and that's where the radicals are going to form. So it's very similar to an allylic position in terms of its selectivity. Now, if I wanted to do this reaction, I could say, well, I'm going to use NBS and heat, and then my bromination would go exclusively, should go exclusively to the benzylic position, because when I form the benzylic radical, that's where the bromine's going to end up, because that benzylic radical is now also stabilized by resonance structures. And if I wanted to react this molecule with, let's say, H2O, first of all, if I took this benzylic bromide and reacted it with water, what mechanism am I going to do? SN 1. Why? It's going to form a carbocation, which will make it SN1, but why does it have to go SN1? Because water is what kind of nucleophile? Weak. And weak nucleophiles can only undergo SN1. They can only react with carbocations. So this would have to be an SN1 mechanism. So that means that I would form my benzylic carbocation. And benzylic carbocations, that's the special place to form them because that carbocation can now be stabilized by resonance. So I could take this pair of electrons, move it out here to start forming the resonance structures. Which would look like that. And then that's basically, all of these are allylic-like carbocations, so now I could move this pair of electrons here, and that's going to form another resonance structure. So I'm going to form that resonance structure, and then I can move this pair of electrons here. To form that third carbocation. So the benzylic carbocation is stabilized by the ability of the ring to basically delocalize the positive charge. So the ring can absorb some of that positive charge. And this movement of the pair of electrons out is sort of what we saw last week when we talked about the benzene ring being an active, I had to use the term activating group, but being an electron donating group by resonance. It can do that. But there is a little wrinkle here, and that is that I could also take this benzene ring and I could say, you know what? I don't have any NBS, so let's give it a shot and let's do the reaction with bromine light at room temperature. And I would be perfectly fine doing that because what I would end up doing is I would end up brominating in the benzylic position, and I would not have to worry about adding the bromine to any of the double bonds in the ring. So when you're looking at trying to brominate a benzylic position, now we can, just to confuse the issue, now I don't have to use just NBS, I could use bromine again. So why? Well, number one, bromine and a benzene ring is a no reaction. KMNO4 and a benzene ring is no reaction. HCl and a benzene ring is no reaction. Because the benzene ring is super stable because it's starts with A, aromatic. So I don't have to worry about the bromine adding to the benzene ring because the benzene ring is super stable. If I come over here and I look at all these resonance structures that I just drew, yeah, they're fine. But what happens, usually when we add Br2 to something, right, we could say, oh, well, could a nucleophile come in and add to that carbocation or this carbocation or this carbocation? It could, but what happens? I've destroyed the aromaticity of the ring. Well, that's not going to happen. So the reactions that we're going to do inside of the ring are all going to be with different reagents. And none of them will be addition, they will all be substitution. So in other words, I'm going to reform the ring by losing a hydrogen off the ring. So we'll get to that. But the reason I can use bromine without worrying about adding to any of those carbocations is because those carbocations are all going to basically not react, because if they did, then my superstable benzene ring is gone. And that doesn't want to happen. So in this case, you could use either one. But the special position is the benzylic position. With the only new wrinkle in it, there's no kinetic and thermodynamic products, because you're not going to add anything in the ring. Okay? So this is that's the major resonance structure. Now the other ones contribute, which makes it more stable than your average secondary carbocation. And that I believe. Okay. So why did I start with allylic? To go back and review that or bring us up to speed on that. But it's a perfect lead-in now to benzylic positions. So when we do things on the side chain, when we do our reactions on the side chain, we're going to be concerned about the benzylic carbon being the one that reacts. Why? Because it's the one that's going to form the carbocation, and it's going to be the one that forms the radical. Why? Because that radical or that benzene or that carbocation is stabilized by the ring. But the ring, nothing's going to add in the ring yet. Okay. So that sets up all the side chain reactions we can do. Is everybody come with me? So, let's see. So what else can I do to the side chain? How about a new reaction that you either did in lab or you will do in lab tomorrow? And that is, where'd my benzene ring go? So if you have any kind of carbon chain and you react this with KMnO4 and heat, you end up oxidizing that carbon and forming a benzoic acid. So whenever you have a carboxylic acid attached to the benzene ring, that would be called a benzoic acid. There might be some substituents attached to it, so it will be something benzoic acid, but in this case, that's a benzoic acid. What are we doing in lab this week? Or what have you done? You have taken we basically protected the amine in the anthranilic acid to form the amide. And what we're going to do is we're going to now react that with KMnO4 to make that methyl group into a carboxylic acid. Then after break, we're going to take away the acetyl group, we're going to take away the amide, we're going to turn it back into an NH2. Why did we turn the NH2 into an amide to begin with? Because KMnO4 might turn the NH2 into an NO2, and we'll talk about that reaction in the days to come. So we have to kind of protect that NH2 with something that won't react with KMnO4. So that's what you did this week, was you converted the CH3 to a carboxylic acid. That's what we're doing tomorrow. And that's what we use the purple KMnO4 with, and then KMnO4 gets turned into MnO2, which is manganese dioxide, which is the brown precipitate, which I believe you have to filter through through the C-light plug to remove it. And then make sure there's no more purple color left. So that's what you were doing this week. It doesn't matter how long the chain is, and it doesn't matter what the chain is. That carbon, whether it's 100 carbons, whether it's an isopropyl group, whether it's an ethyl group, it all gets converted to a carboxylic acid. So if I started out with, I think did we use xylenes in the Diels-Alder reaction? So the xylenes, there's an ortho-meta-para-xylene, and then there's xylenes, which is a mixture of all of them. If you take xylene, in this case we're using ortho-xylene, and we react it with CaMnO4, we can actually, we'll convert both methyl groups into the carboxylic acid. So we'll make that one, which is called, this is called phthalic acid. PHTH, phthalic acid. So if you start with orthoxylene, you'll make phthalic acid. There's phthalic acid automatically, I believe, means it's ortho. Now, if you deprotonate one of these, just because you've seen a form of phthalic acid before, if you deprotonate one of the oxygens, usually with a base to make potassium, that reagent is called potassium hydrogen phthalate, which is abbreviated as KHP. So if you've ever standardized an acid or a base, usually we standardize the bases, like you did if you took Faith, or if you're in analytical, I'm sure you'll do that at some point. You'll standardize your base. If you go on to PChem, you'll have to standardize your base, but they won't tell you to do that, so you'll have to remember that. But that KHP is our primary standard that we use to determine the concentration of the base. And then we use the concentration of that base to determine the concentration of our acid. So I'm sure you did that in general chemistry lab. Here, you might have done it in honors as well. But that's how we standardize a base, is using that KHP. That is just simply one deprotonation off the phthalic acid. And where does phthalic acid come from? It comes from CaMnO4 oxidation of the xylenes. Where does xylenes come from? Coal. All the benzene compounds come from coal. So that's the oxidation. And again, it doesn't matter whatever the group is, it gets converted to a C double bond OH. So whether it's methyl, whether it's isopropyl, doesn't matter what it is, that carbon gets turned into carboxylic acid. So that's a side chain oxidation. That would happen with chromium as well. So in the future, we'll have to think about that, because if I have like a double bond off one part of the benzene ring and I have a methyl group and I want to say, oh, I'm going to cleave the double bond with like CaMnO4, then the methyl group that's off the ring could also react. So when we get to multiple functional groups, we have to think about protection and all those things. Okay. So that's side chain oxidation. Right? That's what we're doing in lab. Is there a mechanism for that? No. Just remember it. Okay. If you haven't broken out 3x5 cards, it's probably a good time to do that, because we're going to be going through a lot of different reactions. Let's see, reductions of ketones. So another reaction that we can do is, and we'll talk about the precursor to this, is I can convert a benzene ring, and we'll talk about this on Friday. I can convert the benzene ring to what's called a phenyl ketone. Now, in terms of the terminology, benzene is C6H6. When you have a benzene ring that's a substituent, we call it a phenyl group. And so this would be called a phenyl ketone because one of the groups that's attached to the carbonyl is a benzene ring. Now, we'll talk about the reaction to make this on Friday. It's called Friedel-Crafts acylation. But once I make a phenyl ketone, there are times when I want to reduce it down to a couple of things. So I could say, well, I want to take that phenyl ketone and I would like to reduce it down to an alcohol. So it's going to be a reduction reaction because I'm adding 2 hydrogens. And then I would ask you, okay, what kinds of reagents could I use to reduce that ketone down to an alcohol? And you would say, usually at this point I hear a lot of notebook page flipping, but maybe we've given up on that. Lithium aluminum hydride or NaBH4 and then H plus. The evil thing about side reactions, benzene side, alkyl group side reactions is I could make the course completely comprehensive at this point. How could I do that? Well, let me just might as well work my frustrations out on this. So let's say I said, hey, give me the reagents to do that. We don't know this one yet. We will. All right, how do I go from ketone to alcohol? Lithium or sodium borohydride. How do I go from, oh, I can do lots of things with that alcohol. I could convert it to a Cl. I could convert it to a double bond. Once I have this chloride, what could I do? I could do Grignards on it. I could do E2 on it, but then again, if I do E2 on it, and this, if I try and do E2 on this chloride, the double bond is going to have to go here because there's no beta hydrogen there. That's the reason why I always try and write out the single and double bonds, because if you put that circle there, you forget there's no hydrogen there, and then all of a sudden you made 5 bonds to a carbon, which is still not legal. So I could come on, it's smaller. I could react that with magnesium and all those reactions. What can I do to a double bond? Oh, I could do everything with the double bond, right? I could add Br2 to it, HCl, HBr anti-Markovnikov. Make an epoxide out of it. What can I do with the epoxide? All the epoxide reactions. Where am I going to open it up? On the benzene ring side? Am I going to open it up on the other side? So I could do all these side chain reactions. I'm not saying that right now to go, oh my God. I mean, I have to remember that. Well, that's midterm. The next midterm, we're going to have the big final. So, yeah, it should be helpful to remember that. But we'll talk about these things. But I could do lots of side chain reactions. So if I wanted to, I could invoke the entire semester of reactions, which I kind of just did by putting them on the slide. But if I decide not to do that, there are some important things that happen here. So for instance, what would I use here? Yes, you're correct. H2SO4 and heat. So sulfuric acid and heat would do the addition, or would do the elimination to form the double bond, the dehydration reaction. I'm going to form the most substituted double bond. Let me rephrase that and say I'm going to form the most stable double bond. In this case, there are no beta hydrogens here. There are beta hydrogens there. I have no choice to put a double bond there. I have no choice. But the most stable double bond in correlation to the ring is always going to be when the double bond is conjugated to the ring. Okay, so that's something that we want to remember. Benzylic carbocation is special. The double bond in conjugation to the ring is also special because both of those are really stable. If I wanted to add Cl, what would I use? I can use PCl3, SOCl2. Could I use HCl on this? Why not? I add HCl, I add to the OH, the water leaves. What kind of carbocation do I get? Benzylic. What's special about benzylic? It's special because it's super stable. And then the Cl minus comes in, so I could add HCl or PCl3, SOCl2, any of those reagents. Good thing I remember these things. How do I make the epoxide? RC double bond OOOH, the peroxy acid. So I use a peroxy acid to make the epoxide. I could use PCl3 or SOCl2 or HCl. And up here I could use H2SO4 and heat. Okay, I'm sure everybody had those right at the tip of their tongue, but if not, that's what I can do with the side chain reactions. Maybe we'll come back to the epoxide ring opening. Maybe we'll come back to that. Because remember, the benzylic position is special because that's where the carbocation forms. Okay, we'll come back to it. So these are all the side chain reactions I can do. So I think I've shown you this reaction before, now it's relevant. So this is Brian Kistler's research project for his honors thesis that he asked me last night. I need a really good title for this. Like, why? But I guess for a celebration poster. So if you can come and grill him on this if you'd like. Back when it happens in whatever, March or April. So we did this because it's not clear that if I add the H plus, where I should add the H plus to this double bond. Because if I add the H plus, I am up against putting the H plus there, which would form a tertiary carbocation, or adding the H plus to the tertiary position and then forming the allylic the benzylic secondary carbocation. And so we can only find one instance that this reaction, the product of that reaction, has been reported. It was just reported in December after we did it. And they said, the Japanese research group said, well, if you add H plus to this, you're going to get Markovnikov addition, which is true because there's an H here and there's nothing there. So the chloride, is either going to add to the tertiary carbocation or it's going to form to the secondary carbocation. So they did this reaction by doing a little bit different than I would have. We were putting it in solution and then adding the HCl, and this is where it takes a week to get the reaction to go, which told me that these reactions on paper are really nice, but in reality they take a long time. And so what they did was they added the HCl to a silica gel, and then what happens is that the silica gel absorbs all the water out of the HCl solution and makes HCl gas in the container, so when you add the double bond, you just stir everything, and basically the gas adds to the double bond. And they got the addition, the Markovnic addition. And so they were just kind of matter-of-factly going, oh, that's the Markovnic addition. No comment, because they did like 15 other compounds to show that you could use the silica gel. But when we did this reaction, we also got that product, which last year I would have written that probably I would have said, oh, well, this is allylic with resonance structures, right? Secondary, that beats it. Apparently not. So this is when Brian said, I don't believe anything you taught me in organic chemistry last semester when we first did this. And I said, yeah, I'm beginning to wonder about that myself. So maybe that's what will make the title. I don't believe anything I learned in organic chemistry. So it appears that this is more stable, the tertiary is more stable than the secondary. Allylic, or secondary benzylic. Now you might say, hey, you need some controls for this. But this is going to be a nightmare to publish, because there's going to be, I would like to give this talk to a bunch of other organic people and then have them like fisticuffs break out as they're trying to argue which one is going to form versus the other. Just sort of pull them and have them argue amongst themselves and we just sit back and laugh. That would be really cool if that would happen. But proving this is going to be a nightmare, because what if that reaction somehow goes by a free radical mechanism? Then I get the product I expected, because then the secondary is then I'm forming this radical with the Br atom here, with the Cl atom there. So we have to completely rule out the free radical mechanism, which I'm not quite sure how to do yet. Well, I do, sort of, but that's going to take a lot of work. So you might say, how about controls? Because that'll always get your paper rejected if you don't have sufficient controls. So how about we do this? How about we say here, let's take that molecule, and all of these molecules are what are called styrenes. Whenever you have a double bond attached to the benzene ring, that's a styrene. Polystyrene, right, styrofoam cups. There's a lot of junk plastic made out of polystyrene. So these molecules will tend to actually react with each other and make long chains, which is the first thing we found out when we added sulfuric acid to it. It turned like brown, and then stuff started falling out of solution. I'm like, oh, it's polymerizing. So we have to be careful with that. Can't shoot that into a GCMS, because as soon as it hits the injector, it polymerizes, and I coat the inside of my injector with plastic, which is not going to work well for Dr. Severino when he injects his whatever, he's cute little frog toxins and stuff. So we do this, we say, okay, secondary versus secondary, fair test. What do we get? We get exactly what we would expect. So if it's secondary versus secondary, it's a fair game. So what's the intermediate here? I'm assuming the intermediate here is this secondary allylic or secondary benzylic carbocation. So that tends to tell us, okay, what you're doing isn't necessarily have a free radical component. It's doing what it should. Secondary allylic or secondary benzylic should beat secondary non-allylic, and it does. And then you might even say, well, let's just get our hands on some styrene, which is just the double bond here, and let's do the same thing. And if we do that, then we definitely end up with, now it's primary versus secondary. Secondary wins whether it's benzylic or not. So controls are fine for this. It's just when I try and look up what people have done with tertiary versus secondary allylic, everybody's giving me the arguments of why this one versus this one or this one versus this one, but nobody's, other than these Japanese people, have done it. So we have to figure out which carbocation is more stable. We have to rule out free radical halogenation. That's all. And we're using deuterium because it does special things in the NMR. Like it couples to the, when you put a deuterium on a carbon, have you guys seen the three little peaks in your carbon spectrum that everybody wants to assign? I've assigned them in my homework problems. I've written solvent because if I don't, then people don't know what they are. There's three little peaks from the CDCl3. One deuterium splits a carbon into three. Won't give every reason why it does. So we can actually track where the deuterium goes in our carbon spectrum. We just can't GCMS it because as soon as we throw it in, it'll polymerize. So the benzylic position is very stable. Apparently, except when you put it against a tertiary. Right? So this is the nature of mechanistic chemistry. No one's going to care. Well, it'll be an oddity. It'll be one of the other oddities that I always find. So, well, that's going to take a while to work out. But I would have just moved on, but then I'm like, we got the wrong one. Which is telling us that's the nature of research. Sometimes nobody's done this, so they're, and the Japanese people were just like, oh, it's Markovnikov addition. That wasn't the point of their study, but and we started it before them, so it gives me a little bit of consolation that we were kind of ahead of the game there. But it's going to take a lot of work to rule out the free radical. But then will the free radical tertiary be more stable than benzylic? I don't know. My unpublished research is supposed to inform my teaching. There you go. That's an example. One of very, well, I've talked a little bit about it. So the benzylic carbocation is stable. If one wanted to bring in kinetic and thermodynamic into this whole debacle, I could do it with this problem. Which I will not make due on Friday. I will not make due after we come back, but I may ask you to do this, to write the kinetic and the mechanism in kinetic and thermodynamic products as the next take-home practice, or as the next graded practice problems. And our key thing here is going to be, our key things to think about are, when the double bond is conjugated with the ring, that's going to be more stable than not having it conjugated with the ring. I'm going to have to modify this. Having the carbocation on the benzylic position is more stable than having the carbocation not on the benzylic position, as long as it's not tertiary. Let me just end with one. end with the epoxide, and then we'll start with this on Friday. I'm going to go over the free radical, or the electrophilic aromatic substitution reactions on Friday. The ones that were in the bottom of the reading today, we're going to do that on Friday and pick up all of the other ones. So, but this one. Think about for Friday, or if you're not here Friday, and you, again, are not in an undisclosed place where you have the ability to at least browse the first part of the video on Friday. Where's the chloride going to add? And why? And your choices are going to be the chloride's going to add to A, B, or 50-50 A and B. Using the key principles of double bond and conjugation with the ring is stable, benzylic carbocation is stable as well. So we'll start with this on Friday, and then we'll do electrophilic aromatic substitution. If you're not going to be here, again, there won't be a quiz. If I get the exams done, then I'll send out an email if you want yours. I'll scan it to you. I will not place the scores online. And if I don't get them done, you'll get them after break. So hopefully the suspense won't spoil your break. Right, but I will be having class on Friday. I will be taking bets on over and under of the number of people that show up. There will be no prizes, but it'll give you an opportunity to, you can influence the result of that. Okay? If you have any questions, put them on Piazza, send them to me.